Hi y'all. We're going to do an independent samples t-test together by hand. And I'm just going to record as I do it here on my iPad notebook. So here's the question. A researcher asks if people score higher or lower on a questionnaire measuring their emotional well-being when they are exposed to too much sunshine compared to when they're exposed to too little sunshine. That's the wrong two. It should be T-O-O, both of those times. This is what happens when a statistician writes a textbook. Let me do that again. A researcher asks if people score higher or lower on a questionnaire measuring their emotional well-being when they are exposed to too much sunshine compared to when they're exposed to too little sunshine. A sample of 8 people is measured under both levels of sunshine, and that produces these well-being scores. So we have a group of low sunshine, and we have a group of high sunshine. And then it says, subtracting low from high, what are your null and alternative hypotheses? Compute your T obtained, and with an alpha of 0.5, what do you conclude from this study? Okay, well the first thing we should try to figure out here is what kind of hypothesis this should be. A researcher asks if people score higher or lower. Higher or lower. That is a two-tailed test. In fact, it's the textbook definition. They're not saying whether the score goes up or down. They just want to know if they're different. So what we're looking here for here is hypotheses that are either high. Forgive me, my security camera's distracting me. We want to determine here whether too little sun or too much sun manifests in differences in these well-being scores. That should prevent my security cameras from bothering us, I think. So we have the group of scores for the low, we have a group of scores for the high. Let's do that null hypothesis and alternative hypothesis first. The null hypothesis would be what we would expect to find if sun had no effect on well-being scores, that it didn't make any difference. So it might look something like this. Mean 1 for low, let's call it mean low, so we're even clearer, doesn't differ or is equal to mean high, because sunlight had no effect on well-being scores. Now the alternative hypothesis would be the opposite. One of the things I showed you in class that caused some confusion is you can do this, not M low equals M high. But my statistics professor in graduate school used to call that tacky, meaning just say it the way you mean it. What we're saying here is that M low does not equal M high, meaning the amount of sunlight resulted in a difference in the scores between low and high. We can calculate the means for low and calculate the means for high and see if they're the same, but that won't really do it for us, because what we need to do is to make sure those scores really differ by creating a standardized score called the T obtained, putting it on a distribution and seeing, is this difference real, or is this difference really just because they were never the same to begin with? Is it just due to sampling error? So, as it says, for B, with this labeled as A, we have to calculate T obtained. Scrolling down here, I have your formula. And these will look familiar to you from the lecture. And I actually walked you through each of these calculations in the lecture, but I wanted to do some of the arithmetic together. And we'll do some more of this together on Thursday. But you can see our T obtained formula is very easy. M1 minus M2 divided by the standard deviation, what we're calling the standard error of the measurement. SD x minus x. Or excuse me, the standard error of the difference, forgive me. The standard error of the difference is equal to the square root of the pooled variance times 1 over n1 plus 1 over n2. And then you see the formula for pooled variance, n1 minus 1 times the variance for 1 plus n2 minus 1 times the variance for 2 all over n1 minus 1 plus n2 minus 1. But the first thing we need is we need the sample means, and we need the standard deviations. So, I don't want to go through both of these standard deviations together. Probably. We've done this now since last semester, but I will do one just so you can see what this looks like. So the low scores, we have 14, 13, 17, trying to stay neat here so it makes it easier for you and for me. 18, 17, 14, 16. Okay. This is our x column. We also need an x squared column, which will be these scores squared. We need to sum these x's here. We need to calculate the average of the x's here, which is sigma x divided by n. And we also have to calculate sigma x quantity squared, which will be the sum of this column squared. We're also, over here, going to calculate sigma x squared, which is the sum of this column. We also need our n size, but that's easy enough to figure out. We do these things, and we've got everything we need. So, I didn't pull my calculator out. I should. So, boo on my recording program because it won't let me have multitasking happening while I'm recording because it changes the size. So I went through and did this arithmetic without you seeing it, but you can see here I've got 14 squared, 13 squared, 17 squared is 289, 15 squared is 225 all the way down. Then I sum that column, so 196 plus 169 plus 289 plus 225 plus 324, so on and so forth, all the way down to 256. So we get sigma x squared equals 1944. I sum the x column, I get 124. I square 124 to get 15,376. And then I get the mean, which is 15.5. Maybe I should do this. I sum these columns to get this. And I square this number to get this, which is the sum here. I know we had a discussion last time we met about getting these confused, and it is the thing that's most easily messed up. And even though we've had a lot of practice, a lot has happened in between our practice. So there you have it. Okay? So if you're going to calculate your SD for low, equals sigma x squared minus sigma x quantity squared over n, all over n minus 1, square rooted. Okay? So we just simply have to plug in our values. So we have sigma x squared is 1944 minus sigma x quantity squared, which is 15,376, divided by our n, which is 1, 2, 3, 4, 5, 6, 7, 8, divided by 8, all over n minus 1, which is 7. And we take the square root of that whole thing. And if we do that arithmetic, we end up with the square root of 3.14, which is equal to a standard deviation for low of 1.77. Standard deviation of low, 1.77. Now, I went through and did that same math for high, and you would do the exact same thing, but I won't walk through those steps. And you end up with a standard deviation of 2.997. More decimal places than probably necessary. So our standard deviation for low is 1.77. Our standard deviation for high is 2.977. Let me take these values and plug them into, I should also say that we have the mean for low equals 15.5. And the mean for high, I also calculated that, of course, which is 18.12. Fixing my 8. Okay? So with that, we can plug in, bring back our formula. Let me just grab them. The first one, we'll get them all. The first one we'll grab is our original formula. Add that. Bring that down, you can see. We need the means, we have that, and then we need the standard error of the difference. How do we get the standard error of the difference? The standard error of the difference is this. Right here. Which is our pooled variance, square root of our pooled variance times 1 over n1 plus 1 over n2. So how do we get our pooled variance? We grab our final formula, which is this one here. And as I said in the PowerPoint, the pooled variance is really just combining those two variance scores. so that we can use them at the same time, and then adjusting them for n size. So with those numbers, we can start actually calculating the t obtained. So we have that t obtained formula here. I remind you it's m1 minus m2 over the standard error of the difference. To get that, we need the standard error of the difference. The standard error of the difference is here. To get the standard error of the difference, we need the pooled variance. The pooled variance is here. So the way we do this is we do the pooled variance first, we do the standard error of the difference second, and then finally we do our t obtained. And then once we've done that, we can compare it to our t critical once we've figured that out. Okay? So let's start with that pooled variance first. Pretty easy, actually, if we're careful with our arithmetic. We've got SD squared pooled equals n minus 1. Our n's are both 8, so 7 times variance, which is SD squared. SD low squared is 1.77. Excuse me, SD low is 1.77, so 1.77 squared plus 8 minus 1, 7 again, times 2.997 squared divided by n1 minus 1, 7, plus n2 minus 1, 7. So let's do it real fast. We've got 1.77 squared, so times itself, gives us 7 times 3.13 plus 7 times 2.997 times itself gives us 8.98. I had that one written down. All over 14. So 7 times 3.1329 equals, 7 times 3.13 equals 21.91 plus 7 times 8.98, which is 62.86, divided by 14. 62.86 plus 21.91 equals, divided by 14 equals 6.055 is our pooled variance. Cool. Oh, I see. Oh, sorry, I was talking to myself. I said, oh, I see, because I just realized something, but that doesn't matter. So we have that pooled variance. Now that we have pooled variance, we can plug that in here to get our standard error of the difference. I'm just going to grab this and move it down so we can see. We're going to plug that pooled variance in there. Let me erase my scribble. And it's pretty straightforward, yes? Standard error of the difference equals the square root of 6.055 times 1 over 8 plus 1 over 8. Forgive my handwriting there. Or square root of 6.055 times 0.25, right? Because 1/8 plus 1/8 is 2/16, which is reduced to 1/4, which is, of course, 0.25. So let's do 6.055 times 0.25 equals 1.51. We have to take the square root of that. And that gives us a value for SDX minus X equaling 1.23. Just like that. Now you can see some earlier work I was doing here. Let me erase that because we don't want to confuse things. In fact, let me erase that as well. So we have basically everything we need. Let me grab our big formula one last time. Just drag it down here so we can look at it. We know that our means are 15.5 minus 18.12 divided by 1.23. So let's see what we get. Our t obtained equals 15.5 minus 18.12 equals minus 2.62 divided by 1.23 gives us a value of negative 2.13 T obtained. And I happen to know that that is correct. So, cool. That's our T obtained. Now, what do we do with it? What we do with it is we compare it to our T critical. And to do that, we need our critical table. So let me grab it. You have family photos, you have party photos, you have pictures of your dog. I have T tables. Let's give ourselves a new page. I can make this bigger. Let me just jot down a couple of things. Well, I don't even need to do that. Let me just stretch this even bigger. There we go. Our test is a two-tailed test. Our alpha is 0.5. So we are coming to right here. Now our n is n minus 2. Each individual n was 18. So that means 18 minus 2 or 14. So let me use my highlighter. 14. So we're going to follow 14 all over to here. And we end up with this value. My highlighter was so fat, it wasn't all that helpful. 2.145. 2.145. So our T critical, 2.145. Our T obtained, oh my goodness. Sorry about that. Our T obtained equals negative 2.13. So this is plus or minus, I should remind you. Forgive me, my text app is supposed to be blocked, but it's not. I'm sorry for that. It's obnoxious. So here's our distribution of the null. Hey, look, that's a really good distribution of the null. Trying really hard to get a smaller pencil, but it will not let me. Our T critical, plus or minus 2.145. This is 1, this is 2. It's going to be very close to that. This is 1, this is 2. It's going to be very close to that. This is 2.145, 2.145. Our T obtained is a negative 2.13. Holy cow. Negative 2.13. I'm going to change the color because this is so dramatic. Falls right here. 2.13. Now, it sounds like I'm acting like I'm surprised by that. I actually am surprised because I didn't do this part of it in advance. So, if we're looking at our region of rejection, it's here and here. Our value, our T obtained, falls outside of that region of rejection, just barely. Look how close that is. That is shockingly close. Rounding error close, which makes me nervous. Nevertheless, because it lands there outside of region of rejection, we fail to reject the null. And so what we're saying is it's not statistically significant. We say T 14 equals negative 2.13 comma P greater than, whoops, I don't even know how I did that. It's cool though. Greater than our alpha, which is 0.5. Huh. What an adventure. Let's do this problem again in SPSS. I'll show you how to do it. It'll give us an opportunity to check our work as well. Hello. It's been a good long while since I have used Zoom to record a thing. I've been trying to do it in what I would argue are better ways, but for something like this, this is probably the best way to do it, which is to show you how SPSS works. Specifically in the context of independent samples t-test. We've just calculated an independent samples t-test by hand. And to remind you what the research question was whether high amounts and low amounts of sunlight manifest in differences in mood. So we had one condition that had low levels of sunlight, one condition that had high levels of sunlight, and we measured their mood afterwards to see what we found. Now in that calculation by hand, which just happened, it was not significant. It was close. It just missed meeting that region of rejection. But let's see what we see when we do the same calculation in SPSS. So I remind you that in SPSS, we have two views. We have the data view and the variable view. And I'd highly recommend to you, again, just like I did last semester, start with your variable view, because this is where we're going to create our variables. Now, in a simple experiment like this, we have two, right? We have our dependent variable, which is mood, but we also have our manipulated variable, our IV, which in this case is amount of sunlight. So let's put sunlight as our first variable and mood as our second variable. Sunlight is our independent variable, so we need values. Click on this button here, and we're going to say that low amounts, low sun, oh, excuse me, I'm doing this wrong. The value is 1, excuse me, and that will represent low sun. And then 2 will be high sun. I accidentally hit Siri. Add that, click OK. And then mood is going to be our DV. Okay, so we click back over here and we'll see sunlight and mood. And the way we're going to do this is to go one at a time. So this will be 1 representing our low condition, low sunlight condition. And if you go to view value labels, you see that 1 stands for low sun. Okay, go back, take that away. The first participant in low had a score of 14. The second participant in low had a score of 13. The third, a score of 17. You see how this works. Forgive me as I make mistakes along the way. 17, then 15, then 18, then 17, whoops, 1, and then 17. We're getting all of our first level of our IV listed here. Now you could do them back and forth if you wanted to, but I just think it adds to confusion. So we've got 14, 13, 17, 15, 18, 17, 14, and 16. That's right. Now we're going to start on the high sun group. 18. Second one is 12. The third one is 20. The fourth one is 19. And we'll just keep on going. Check my work as I go here. 19. Easy to make a mistake while you're transcribing, going back and forth from paper to computer. In fact, this is the second time I've done this video because I forgot to share my screen the first time. And when I did it, I did get some of the numbers wrong. Let's go back to view and then value labels again, and you'll see this should be all of the scores in the low sun condition, X. This should be all the scores in the high sun condition, Y, or X1 and X2, I think is the way we labeled them by hand. Honestly, as is always the case, this is the hard part. Getting the data in there in a way that it is correct. Once it's in there correctly, it's easy to analyze the data. The problem is if you put it in there incorrectly, it's still easy to analyze the data and you end up with garbage. So always pay the most close attention and careful attention to the way you're entering your data. We've got two variables. One is value label for the condition. The other is the DV. Now there's actually more than one way to do independent samples t-test in SPSS, but this is the way that's easiest and the way I want you to do it. Go to Analyze, Compare Means, and the Independent Samples t-test. I want you to see that the paired samples t-test is here. We're going to learn that soon. The one-way ANOVA is here. We're going to learn that even sooner. And also the one samples t-test, which we don't do in SPSS and won't. But we're looking for this independent samples t-test. It's going to open up this window here. It opened up on my other monitor. My apologies. You can see we have test variable and grouping variable. Write this down. This is really important. The test variable is our DV. Okay, so for us, that's mood, and we're just going to shoot that over there. Our grouping variable, therefore, is our IV, so we're going to shoot that over there. I want you to see that when we do, you'll see these little question marks. What it's wanting us to do is identify the order, which one's X1 and which one's X2. Now, the question that we actually were asked us to make high X1 and low X2. We didn't actually do that because it seemed silly and it doesn't matter. So we're just going to keep it the way that we did it by hand. And you can see that I've already done this. We made group 1, 1, and group 2, 2. Click continue. Now those numbers fill in there. Then we simply click OK. And when we click OK, my data went to the other screen. Hang on just one sec, as I'll lift it up there for you. It opens up that data view as it always does. And you can see here, so I make it full screen, you can see our result. T-test. First, you get your descriptive statistics. Our N is 8, that's right. 15.5 and 18.12, that's exactly what we got when we did it by hand. So too of the standard deviations, 1.77 and 2.99. So this looks exactly like it should. Now this gets a little bit complicated. This is your actual independent samples t-test. But there's two things here. Here's the t-test, and here's what's called the Levene's test for equality of variance. Do not make the mistake of paying attention to this when I'm asking you for this. The Levene's test actually tests the assumption of homogeneity of variance. It takes our variance scores and sees if they're the same or not. And in that case, you want something that is statistically non-significant, meaning there is no difference. And in fact, we see that our Levene's test for equality of variance is not significant, which means our test, rather our scores, do have homogeneity of variance. Good news. But what we really want to pay attention to is this, the t-test for equality of means. I want you to see that your t-score is right here. Now you'll notice there's equal variances assumed, equal variances not assumed. We're going to use equal variances assumed because of our Levene's. Truth be told, we're always going to use it. Negative 2.132 is our t obtained. That's what we calculated previously. Degrees of freedom n minus 2, so that's 14. That makes sense. Here's our standard error of the difference, which we calculated. But here's the key thing to pay attention to. Significance value two-tailed 0.051. Remember back to that calculation by hand? It just barely missed landing in the region of rejection. And this too just barely misses being statistically significant. I remind you that we don't have a critical value calculated here in SPSS. That's not how it works. What it does instead is it gives us the probability at which this would be significant. If that value is above our alpha, it's not significant. If it's below our alpha, it is significant. This is 0.051, just so close, just so barely above our alpha, just like it was just barely not in our region of rejection when we did it by hand. So this t-test is not significant. We fail to reject the null. If it had been 0.050, we would reject the null. But because it's above 0.05, we fail to reject the null. It's non-significant. So we would list it, t, parentheses, 14 equals negative 2.132, comma, p greater than 0.05. And it is. It's 0.051, just barely greater than 0.05. Okay? So that checks out. And most importantly, you can see how this works in SPSS. Super easy. Go to Analyze, go to Compare Means, go to Independent Samples t-test, put your DV in the test variable, put your IV in the grouping variable, and then define your groups. Make one of them 1, one of them 2, just know which one it is. Click OK, and Bob's your uncle. Okay? Simple. What we'll do moving forward is exactly the same. Calculate it by hand, understand the statistic, and then we'll come to SPSS and see how it looks. Truth be told, SPSS is how you're going to do these 99% of the time. I believe twice in my career as a professional researcher have I done a t-test by hand. And in both cases, it was because we were in a pinch and we just wanted to see what the data looked like. And so I just knocked it out. It's only because I've been teaching statistics basically every semester since, my second year of graduate school. I assure you that that is not common practice, but occasionally. We do them by hand so that you understand what they are and what they mean. But SPSS is the way you'll do it in real life. Okay, I'm just talking to talk. I have office hours now, so I'll go to them. I'll edit that out because who knows when you're watching this. All right, I'm going to say goodbye now. Goodbye now.